Hello. So, welcome everybody for the 6th edition of PAW. This year we are focusing on AI and audio programming languages. PAW is organized by the Emerald team, grouping people from INRIA, INSA, and GRAM. So, welcome everybody for the 6th edition of PAW. This year we are focusing on AI and audio programming languages.
You have the streaming link.
PAW is organized by... sorry.
Hey, streaming is working.
We are experiencing 5 delay feedback loop. Sorry for that. So it's working. So a few slides to introduce the subject. So as you know, AI is a hot topic, and you probably follow the recent OpenAI saga. AI and music is also a hot topic, and we have tools coming every day almost, and like this tool announced 2 days ago by DeepMind, a set of tools for music creation. And even more recently, we have AI and music programming languages with Force GPT, which is a customized version of ChatGPT tools that you all know. Basically, that allows you to help programming in Faust, so the programming language we have invented at GRAM and that we use a lot in the Emerald team. So it was done by Ollie Larkin. And for instance, with this tool, you can do this kind of thing, like asking Force GPT to help you program a stereo module doing gain with the sliders, and then you interact with the system that explains you the code up to the point where you have hopefully a piece of working code, and you can copy-paste it into the Faust IDE, and it's supposed to work. And you have, well, obviously it's very basic, but you have a stereo gain slider. But it's even better when you have this kind of feature. In ChatGPT, you have also a picture recognition system. But in this case, Ollie Larkin tried to write an audio circuit, have the system analyze it, and try to infer the Faust code for this circuit, which is basically a kind of circuit with a feedback loop. And in this case, the code is still not completely correct. So you have the code on the right, and you have to fix it because, well, it's not correct. But you see the point. In only 1 year, we have this kind of tool, and, well, it's quite exciting. Now, PAW will be introduced by Romain.
Okay, thank you, Stéphane, for this introduction. Welcome, everyone, to PAW 2023. I'm just going to give you a couple of practical information before we begin with the first presentation this morning, which will be given by David Braun. So the first thing that you need to know is that there is going to be coffee breaks, okay? And for coffee breaks, you have to go upstairs, okay? The problem is that we're in a library, there are students working, and they wanted to be quiet in the hall, okay? So coffee breaks will take place upstairs on the 2nd floor. There are signs in the lobby, you just follow them, and then you can go upstairs for this, okay? So please try not to talk too much in the lobby. So that's the first thing that you need to know. Another practical information that you need to know, and I think I already sent you a message about this, is that we're going to have a lunch break. Those of you who are presenting will have lunch here, and the others will have to go somewhere to get lunch. Okay. It is Saturday. We're kind of far from the city center. There are not that many options, but we gave you a couple of options on the conference website where you can go to if you want to get lunch. And mostly they are Ninkasi, Ladois, Univers Café, or this bakery that makes very good sandwiches. Okay, and they're all aware that you might come, so you know they should have food for everyone. So that's the other thing that you need to know. Okay, now talking more about the program for today. So we're going to have 4 presenters. David Braun, who's visiting us from Princeton University. He's doing his PhD on machine learning, Faust and JAX, you know, and so that's what his presentation is going to be about. Then Miller Puget will give a presentation on Predata and AI. Miller is currently based in Paris, so it was very convenient for him to come here this time, and we're very lucky to have him. We'll also have a presentation by Celeste Betancourt, who's visiting us from Stanford University, very far from here in California. Celeste is doing her PhD at CARMA, the Center for Computer Research in Music and Acoustics, and she will talk about live coding environments in the context of AI, mostly about the Chuck programming language, right? And finally, Benoît Carré will give a presentation on AI and music composition. So this morning is mostly going to be presentations, like oral presentations, but then this afternoon we will have workshops. Okay, so basically this morning is like the light version of what's going to happen this afternoon, which is probably going to be way more technical. Anyway, I think this is pretty much everything that we wanted to tell you. We're very happy to see all of you. If you have any questions, you can ask them at the end of each presentations. One last thing, for those of you who are watching us remotely, if you want to ask questions, you can ask them in the chat. And then Agathe, who's our technician here, will relay those informations to the presenters. Okay. One last thing that I want to say: this event is sponsored by INRIA and by Graham, and thanks to their generous donations, it's free, you know, and so we're very lucky to be able to organize this kind of event, you know, open to everyone for basically nothing, you know. You can, and so thanks to INRIA and thanks to Graham for this. Anyway, thank you very much, and we'll start in about 3 minutes. Yeah.
You need that. Yes.
Okay. Hi. Thanks for having me. I'm really excited to be here and happy to talk about Faust and AI with you. Microphone?
Oh, yeah. No, just wait 2 minutes. No, you're very excited.
Yeah.
Yeah, we need to wait.
Okay.
You know, like, 'cause it's streaming, so.
This is the slides URL, the website, so you can see all of my slides right now at tinyurl.com/paw-lyon. Okay, great. So happy to be with all of you today to talk about Faust and AI. As I said earlier, that's the URL for these slides, which will be especially helpful if you're attending the workshop in the afternoon, because the slides have links to some more things, and so you can browse that during the lunch break, and it could be helpful for lunch. So I'm happy to be back in Lyon after 13 years. I came here on vacation with my family, and it's a wonderful city, so glad to be back. Those are me and the Traboul on the left. My background is primarily in real-time computer graphics, and more recently I attended a master's program at CARMA, And there I studied audio and machine learning. That's how I got introduced to Chuck and Faust, which I became very excited about. I managed to pivot that into a PhD topic, which I'm now pursuing as a first-year computer science PhD student at Princeton. But these real-time graphics I made with Touch Designer, which I'm a big fan of, and it kind of ties together a lot of the software that I use, such as Faust and Chuck. But today's topic is mainly Faust and AI. And also the theme of the workshop this year is domain-specific languages, Faust being one of those specific audio DSLs. There is a great history of domain-specific languages for computer music. In this paper from Roger Dannenberg, we have a timeline, and on the right side we see Faust, and we see some familiar friends in here. We see Chuck, and we see Max MSP, and we see Miller Puckett with PD, and all the languages going back in time. But what makes Faust special? Or here are some more languages on the box on the right that are newer DSLs for music. But what makes Faust special? Well, you can browse the syntax page and get a quick overview of Faust. But primarily, it is a functional programming languages. And these kinds of languages have some usual characteristics. One thing is that you can declare things out of order, which is useful. There are also no side effects. When you give the same arguments to a function, you get the same result. And there's also pattern matching. That's very common in functional programming languages. Also, there is the block diagram algebra, which has 5 essential operators. Those are the parallel operator with the comma, the sequence operator, the split operator, the merge operator, and the recurse operator. And so this is essential to what makes Faust a special programming languages, because you're thinking about composing these block circuits or boxes together to make useful audio DSP. It also has a very interesting compiler with intermediate stages, and I'm going to be talking about those things more today. So those intermediate stages are boxes, signals, and the Faust imperative representation. And also at the end of the Faust imperative representation, Faust gets translated into target languages such as C++, WebAssembly, and so on. But I won't necessarily be talking about those. I'll be talking about the intermediate representations like boxes, signals, and FIR. Okay, so a motivating example for the talk today is optimization and machine learning. In this example, we have a low-pass filter, and there is a cutoff. And the cutoff is a value of 440. But what if we don't know that the best value is 440? What if we just have some data set of inputs and outputs, and we suspect that the audio is going through a low-pass filter in order to produce the output audio? But how do we find out that the magic value of 440 is what transformed the input into the output? And this is where machine learning and optimization can play a role. So I'll be talking about that today. A more interesting and complex example is sound matching via machine learning. So this is a recent synthesizer called SynPlant2, and you can provide a short sample of audio, like a one-shot of a synthesizer, and it can almost magically infer the settings of the synthesizer to recreate that sound. And so that is a kind of machine learning and optimization problem. Another motivating example is program synthesis. So here we have that same low-pass filter. There's a cutoff parameter, and I've just inserted some white space in between the start of the program and the end of the program. But what if the cutoff could be something downstream of another piece of code? So cutoff, we might decide, needs to be something that goes into a remap, so that it's something that gets remapped into the output range 440 hertz and 880 hertz. But now we need to decide what goes into this remap. And we might decide that it's going to be an oscillator, but then the oscillator needs a frequency. And we decide, okay, we're going to give it frequency 1, and we're going to give frequency 1 is something that gets mapped into 4 hertz and 16 hertz. And this process continues recursively, and here we decide it needs to be an oscillator again, but it could have been any other Faust function. And then we name a variable frequency, and the frequency now gets declared as a terminal node, which is the slider. So this process of procedurally making programs is a kind of search problem where we might have a specification we want to make an interesting audio effect or to match a certain database of sound, but we have this search procedure via program synthesis to create new Faust programs and see what can be created. Another example on program synthesis is just to be able to kind of recreate an existing plugin. So here, this is a VST plugin from Steve Duda, who's the author of Serum, and on Reddit, he gave this description of what is going on inside the DSP. So you might want to use something like Faust GPT or program synthesis in order to parse this text and then come up with a almost reverse engineering of what is going on in that VST. And that leads me to another topic, which would be reverse engineering of black box models. So in this case, we might have a guitar pedal, but the reason we call it black box is because we may not have a diagram of what is going inside the pedal, and that's why we call it black box. Alternatively to black box optimization, there's white box optimization. So you might have a box and you would have a diagram of what's going inside, but you don't necessarily know the numbers that are kind of the hard-coded constants that go into that system. And so you would use machine learning to figure out what those numbers are. But in the case of pedals, it's just black box. And the reason you might want to use program synthesis is that you could propose many models, many topologies of DSP circuits, and now you use program synthesis to search over many models. And you numerically optimize each candidate model. You may end up finding a more efficient or interpretable implementation than the black box, so it can lead to happy accidents. So now we're going to be transitioning into some of the machine learning aspects more, and one background project on this is the Intro to DDSP with PyTorch. This was recently presented at Izmir in Italy in November. You can visit this URL, which is a very great introduction to the topic of differentiable digital signal processing, DDSP. It was authored by these students from QML, Queen Mary University London. And they also wrote a survey paper, which is a review of differentiable digital signal processing for music and speech synthesis. And in it, they write, rewriting DSP algorithms in an automatic differentiation library can itself be time-consuming and introduces an additional burden to the research pipeline. However, recent efforts have sought to support the translation of DSP code into differentiable implementations. So what they're acknowledging is that this process of rewriting, of having an audio signal processing engineer write that code a second time in a machine learning framework is time-consuming and prone to errors, and they're looking for an automated solution. But their second sentence there gave a shout out to some of the work that I've been doing in Faust and JAX, which is automatic translation from an audio DSL, such as Faust, into a machine learning framework, which is DDSP. So the takeaway point is that people are still manually writing differentiable DSP code in PyTorch, which is time-consuming and error-prone, and they're not taking advantage of the Faust libraries, which already have great DSP code. So I'm happy to share with all of you that there is an automated solution to making this DSP differentiable and scalable, and that solution is Faust to JAX, taking the audio DSL of Faust and automatically converting it into the JAX machine learning framework for numerical optimization. So to recap, the motivating examples were numerical optimization, program synthesis, and reverse engineering. And a pipeline that I am imagining and going to develop more in my research is this one here. So we can start with existing DSP code, or we can use program synthesis to create that DSP code, and we do that in Faust. We can do it at any of the representation levels, which are either Faust code, or signals, or boxes. Signals are actually lower level than boxes. And now we convert that to JAX, and then we optimize in JAX. And we complete the loop by learning from what we've optimized to inform how we do our program search in a better way. Any questions so far? Okay, great. So another overview of the topic today is that I'm going to talk about numerical optimization with Faust and JAX. And I'm going to talk about effects with learnable parameters and effects with learnable parameter automation. And then I'll talk about a subtractive synthesizer and a wavetable synthesizer, and then a newer and slightly improved implementation of the Yamaha DX7 synthesizer. And all of this runs within JAX. It is differentiable. It can be numerically optimized. And then in the latter portion of the talk, I'll talk about program synthesis and how we can generate Faust code, generate boxes, and generate signals. And that can be useful for exploring the space of potential topologies of DSP code. Okay, first topic is numerical optimization in Faust and JAX. So here is a related work on VST plugins and using machine learning to optimize the parameters that you pick. So this is work from Adobe in 2021. It is called differentiable signal processing with black box audio effects. So here, with my mouse, I'm pointing out the audio effect here, which is a Linux LV2 plugin, which is just C++ code that's compiled and it's running on your computer, and you can't optimize it, or you can't calculate gradients of it in a machine learning sense because it's a black box model. But they use gradient estimation with an interesting technique called SPSA, and with that they're able to train a deep encoder to predict the parameters that should be used in order to achieve a certain effect. So if their goal is to make it sound like a professional recording audio podcast, they have a deep encoder that can listen to the input audio and decide the parameters to pick for their compressor and gator and various other effects in order to make the audio sound clean and professional. In practice, the way this works is that they have a sliding window of, say, 1 second, and for that sliding window of 1 second, they are predicting the parameters that are used in a smaller frame within that 1 second. So when you take that 1 second window and you slide it across your entire 60-second, 120-second recording or anything, you are predicting parameters, and you can smooth out those parameters over time, and so you end up with an automation curve. So you get a time series prediction of all of the parameters in your model. Now this is interesting, but it's not using Faust. They're limited by what plugins they have available in LV2, and also they're using gradient estimation, so they don't have access to a kind of ground truth analytic gradient, and that is what is appealing about the JAX implementation, which I'll show with you now. So here we're going to do a very simple example, which I hope that you can learn from and expand into more complex examples. We are going to be optimizing a filter's cutoff frequency. So here we have a low pass, and the value is 440. So it's a magic value of 440, but we're going to pretend that we don't know that in advance. And also, as I mentioned earlier, this is going to be a black box example, or sorry, this is a white box example, because we know what the hidden model's DSP code is, and we're just trying to figure out what that magic number is. So our training set is pairs of inputs and outputs. The inputs are going to be white noise, just full spectrum white noise, and it's going to go to this system, which is a low pass filter, and so then the paired output example is going to be that same noise with a low pass. And our goal is to use gradient estimation to take these pairs of inputs and outputs in order to figure out what the optimal cutoff parameter is. So in this graph on the right, we start with a cutoff value of 10,000. So here on the x-axis we have 10,000, and when we go up on the y-axis, we start with a loss of about 0.3. And when you follow the gradient, you're going to go to the left, and you go down the slope, and you end up with a value of 440, which is the local minimum and also the global minimum. That's not necessarily the case in all machine learning problems. There can be lots of local minima, which makes this loss landscape more challenging, but there are machine learning tricks in order to improve that. So when we plot this another way, on the x-axis we have time, and we see that the loss falls very steadily over time and stabilizes with a loss of 10 to the negative 4, which is close to 0. So this example was just one parameter that we were optimizing. And of course, DSP is more complicated than that. You might have 10 parameters that you need to optimize, or 150, or even 1,000. In this example, which I've linked to, this is another notebook called the QDAX notebook in my Python library called DawDreamer. And this example is a parametric equalizer. There are 3 sections, with each section having a bandwidth in hertz, a frequency in hertz, and a gain in decibels, and then a final main volume parameter in decibels. And so we may not know anything about the parameters in advance, but it can optimize and find the perfect or near perfect solution and recover those 10 parameters in just a minute. So you can check out that notebook, and I may have time to show it in the afternoon. So a more complex example is to do inference of the parameters automation. So we are no longer assuming that the parameter is held constant over the entire recording. This cutoff parameter is like a knob on some module, and we are saying that whoever created the audio could have been changing that knob over time, and we're trying to figure out what the animation was of that parameter. So here in this DSP, I just have a box on the right to indicate that this is a system that takes one input and it has one output. The input here is the signal that is to be filtered, and then the output is the signal that comes out, which is the filtered signal. So I'm just going to refactor this code on the left and put it down here. So on line 3, I just retitle it to be fx, and now I just say that process is the wire symbol sequenced into fx. So it has one input and it has one output. This is the same code, and to emphasize, it's just a signal to be filtered, and the output is the filtered signal. So what we want is actually for the cutoff to not be inside the box. We want inside the block diagram. We want the cutoff signal to be lifted out. And the way we do that is with a new feature in Faust, which is widget modulation. It was introduced in Faust 2.6.9.0. So here, I declare on line 4, replace equals cut in parallel with a wire. And when I use this new widget syntax, I say cut off and replace. And the cut is taking the H slider that exists inside the box and cutting it. And then the wire is introducing a new audio rate input to the system. So we end up with a box with 2 inputs. The first, the thing that I replaced, I inserted a wire here. And so this wire shows up as a new cutoff signal, which is an audio rate signal to the system. An important point here is that the cutoff signal is no longer clipped or clamped between the range of 20 and 20,000 as it was defined by this H slider here. It's now totally unconstrained. So if we're doing machine learning here, we have to make sure that whatever is providing input to our new box with 2 inputs isn't providing a out of range value of the cutoff frequency, because if you were to provide a cutoff signal, a cutoff frequency of 0 or above the Nyquist frequency, then you can have an unstable filter where you divide by 0 or explode to infinity. So this is that same code on the previous slide. And the example that I'm going to show the code of in the afternoon is this example here. So we have the cutoff, and the hidden value of that cutoff automation over time is a sine wave. So we're saying that the person changed the knob or set an automation curve to change that knob in a sine wave pattern going from like 500 hertz to 18,500 hertz. And our machine learning system is able to take just an input audio and just a ground truth audio, and only listening to those 2 things, it is able to recover the automation of the system. So to emphasize, the orange line is not looking at the blue line in order to match it. It has no awareness at all of the blue line. It is simply listening to the generated audio from the system and the ground truth audio, and through gradient descent, it is able to recover and perfectly match the blue line. You may notice that the orange line is a little bit pointy, and that's because it's the number of parameters that the trainable model has is actually limited. We have 1 second of audio, which would be 44,100 samples, but that's a lot of parameters to optimize. So we can actually say, I only want to optimize 40 values, and we can stretch those 40 values with linear interpolation over the 1 second, and then try to match the ground truth signal. So that's why it's a little bit pointy. But if we were to give the model, the trained model, more learning capacity, then it would actually look like this. So this orange line is matching that blue line much more perfectly, and the notebook in the afternoon is going to demonstrate that more. This is the code, so you can check that out later, but I'll cover it a bit in the afternoon. So are there any questions about this so far? Okay. So another example is this subtractive synthesizer. So here we have the basic setup for a polyphonic synthesizer in Faust. We have to declare a frequency, a gain, and a gate. Frequency being in hertz, a gain being like a velocity value between 0 and 1, and a gate being like a threshold of velocity. It's either 0 or 1. We have a sawtooth with the frequency, and then it gets modulated with a volume. It goes to our filter, and then we split it out into stereo. The filter cutoff has a constant value of 5,000, but that is pretty boring for a subtractive synthesizer. We want to introduce a modulation where another envelope can modulate that value of 5,000. And what if that envelope had parameters for its ADSR, and those parameters were learnable? So you would want to use gradient estimation, gradient descent in order to figure out what those parameters were of the envelope that is modulating the filter cutoff. So when we code that kind of example, it would look like this. We have an envelope in the middle section, and we have a range. So the range is 440 hertz to 15,000 hertz, and so we might be estimating the parameters of our envelope that are routed into our filter cutoff. The next example in the notebook for the afternoon is a wavetable synthesizer that is inspired by the Serum VST as well as other wavetable synthesizers. In this example, there is a wavetable here, which is a kind of 2D representation of wavetables. There is a knob here. So this knob is titled WT pause for wavetable position. And when we change this knob, we are linearly interpolating among many wavetables. So when the knob is at 0, we are using the wavetable that's located here. But when wavetable is 1, then we're using the wavetable all the way in the back. This is a very effective model, popular in EDM and other genres, so you can get really interesting growls and wub effects and stuff. So it's really great signal processing technique, and we're going to implement it in JAX. There is already related work on this topic. There's a paper titled Differentiable Wavetable Synthesis from TikTok researchers in 2022. And in it, they are able to recover or take a data set of existing audio and figure out what wavetables should be used in order to recreate those sounds. But one limitation of their work is that they don't share their code, so that is kind of a weak point. Sorry to be critical of them, though, but you should open source your code, in my opinion. But another issue is that they're not using a lot of the other great DSP that exists. So Faust has the Faust libraries, and their wavetable synthesizer isn't necessarily taking advantage of all of the other great DSP that exists in Faust, where you can have distortion effects and echo and so on, and all of those would be differentiable, as I'm pointing out today. So in this example, we have a wavetable synthesizer, and what I'll show in more detail in the afternoon is that we will create wave cycles. So we will use NumPy to save out these time series, where each time series is 2,048 samples to represent a wave cycle. The first one is a sine cycle in blue, and then we have triangle in orange, a square wave, a pulse width modulation wave, and then a sawtooth wave. And so when we use Faust and JAX in order to render this audio in parallel on a GPU, TPU, CPU, et cetera, we are able to generate all of these examples of audio. So one example could be outputting audio that sounds like a sine wave, a triangle, a square, pulse width modulation, and so on and so on. And what is interesting is that the wavetable is learnable. So if I were to provide a set of sounds through gradient descent, we could actually optimize those wavetables, those 2,048 values, in order to recreate that sound. So it's very much like the earlier TikTok paper. But another cool thing is that the interpolation between the wavetables is also learnable. So here, we have this knob, which is like the WT pause slider, and it's a value that goes between 0, 1, 2, 3, and 4. So if it's exactly 0, you get a sine wave. It's exactly 1, you get a triangle wave. But if it's somewhere in between sine and triangle, then you actually get this linear interpolation between the sine and triangle. So you can see at the top, this is sine and this is triangle, but when that parameter is slightly in between, then you get this interpolation between sine and triangle. And when you have some envelope that's modulating that wavetable position, then you can get very interesting sounds. And so all of these sounds are generated and rendered in parallel, so when you have a GPU using JAX and executing this code, you can have 500 plus synthesizers running at once. And as GPU memory limitations go up, as a consumer card goes from 8 gigabytes to 16, 24, and so on over time, I think rendering audio with JAX in the GPU realm is going to be increasingly important. So also on this topic, there is a new implementation of the DX7 that I've been working on. It is we've long known that Faust has a great implementation of the Yamaha DX7, but I noticed some limitations that were documented inside of it. It was missing an LFO. It was missing some things relevant to the breakpoint parameters. So I read the owner's manual of the DX7 and made an effort to improve it in various ways. And that code is now shared at this GitHub repository. But I welcome other people to read the code and improve it further. I made a Python script that can parse SYX preset files and turn them into an aggregate CSV. So you can download for free off the internet like easily 20,000 DX7 presets, and now you can use JAX to efficiently render all of them as like one-shots or with chords with the GPU. So I'm excited about that. And also just acknowledging that the DX7 implementation is still not perfect, you are definitely encouraged to go to this repository and plug in your own synthesizer to come up with your own model, to plug in your own effects and so on, and create your own data set of music, or to just use this as a seed project in your own research. And I'm happy to talk more about that one-on-one if you can find me afterward. Okay, so a general research recipe is to think about the Faust DSP you want to use, pick a data set or make your own, pick an architecture and a learning algorithm, such as stochastic gradient descent, or reinforcement learning and quality diversity. That's a reference to the notebook in the afternoon. You also want to pick a loss function and an optimizer and evaluation metrics. And there are other good ideas in Andrej Karpathy's recipe for training neural networks. Any questions on this? Okay, so latter topic is program synthesis. The question is, can we parse, mutate, and generate at Faust's various representation levels? Those representation levels are Faust code, which we're familiar with and write pretty often, I hope, and boxes, which is a new API that was opened up about 2 years ago, I think, to the public in C++. And there's also a signal representation. After that, there's Faust imperative representation. But my personal opinion is that this is possibly too low level for machine learning. You wouldn't want to manipulate it at this level because it's just too low level and not abstract enough to come up with useful kind of mutations. And similarly, the backend level I don't think is relevant for our interests because it's a totally different language representation. So we're kind of audio DSL engineers, and once you turn it into C++ or Rust or any other programming language, it's no longer an audio DSL. So it's a little less appealing. Okay, so the first topic is generating Faust code. This is a slightly complex example. And I'm not giving away, unfortunately, all of the code yet to this, but I just want to talk people through it. So here we're using the component syntax in Faust in order to load from a local file. And now once we've loaded our local file envelope, it's going to take, this is a DSP function that takes some number of operators. And you, as the programmer, coded this envelope.dsp file, so you know the number of operators that it takes. So you load all of your preset operators and things. You also load all of your components. And now what you need to do is, if your topic is modular synthesis, which is one of my main interests, then what you want to do is compose all of these components together. So you know exactly how many arguments each function takes, and it's just up to you to come up with a generative system that composes all of these functions together in a reliable and predictable way, but with some generative capacity. So the formula here is that you would want to make a basic DSL abstraction of Faust code. So Faust code is already a DSL, but what if you make a DSL layer on top of Faust? And now you make a compiler for that new DSL that you've created, and you go to Faust. So to recap, you start with some set of Faust components, then you build some examples with your components just for practice. Now you create a DSL for your task. That DSL can be a form of YAML, JSON, Python dictionary, or anything else you come up with. And ChatGPT is especially helpful for teaching people like myself about making DSLs. So you can use things like Antler and Lex and Yak and stuff, and you can get creative in terms of making your own DSL on top of the Faust programming language. And things like JSON and Python and dictionaries and things like Faust GPT is really excellent at that. So it'll have some interesting suggestions for you. Then you create a compiler from the DSL to Faust, and then you create a generative mutation procedure for the DSL. And once you do that, you're able to have generative Faust code. So related to this, the next step is generating boxes. Boxes are this intermediate representation of Faust, and I've created Python bindings to boxes. So I have a GitHub repository called DawDreamer, which you can install with pip install DawDreamer, and there are links to this in the slides. And there is this page that gives an outline of the different box functions. So once you import DawDreamer, then there are these things there that are equivalent to what you see in the box API in the C++ version of Faust, but these are just Python bindings to those functions. So you can compose boxes via Python. So you're interacting with this raw and powerful intermediate representation of Faust, but you're doing it via Python. So when we do that in Python, we can write Faust code as just plain text, and now we can convert from a box, we can take our DSP code and turn it into our box. So this box has one input, which is the wire, and the output is just one because it's the result of an addition. So we can assert that our box that we've created has one input and one output, and we can do this in an equivalent way. So here, instead of going from box from DSP, we can just use these operators. So we create a box wire, and we have 3.14, and we add it to our wire. So the result is a box that also has one input and one output, just like the code at the top. And now it's possible to convert our box, which we've scripted via Python, and we can turn that into JAX code. Once it's in JAX code, then you can numerically optimize it, just like those examples that I was showing you earlier about cutoff. So it would be interesting to have more people get practice with the box API and have generative procedures for composing boxes together and see what kinds of crazy stuff you can come up with. So as I said earlier, once we have our JAX code with it, which is Python code, we can actually execute that in the global scope in Python, which is a little bit of a security risk, but you just have to trust me or whoever else that the JAX code that you've generated is safe, and you can extract the class from the global namespace, and then you can use that just as if you had written class myDSP : and so on and defined it like a regular class. So this is the technique of generating boxes. Earlier I showed you one way, which is to call box add, and box add takes 2 arguments. But here, we are actually overriding what's known as a dunder method in Python. So in dunder, it's like an object can have a function like that's 2 underscores, add, and then 2 underscores again. So when you override that argument, as I've done in my C++ bindings, we're able to make it so that you can just call plus on these objects. So this is another way of creating this box that has 1 input and 1 output. Another interesting thing you can do is an in-place operation. So we can say plus equals box real, and we can also implicitly cast 5 into box real. So box plus equals 5 works, and that 5 is automatically cast into box real, which is a floating point number, real just being the same meaning as floating point. So another cool thing about boxes is that you can use the techniques that I mentioned earlier about components. So suppose we have cool component.dsp, and in it we have this constant, which is size. When we call box from DSP, we can make a reference to a local DSP file on disk called cool component.dsp, and then we can override the parameter size equals 3. And when we specify a path to our directory, which holds this cool component file, now our box here is actually going to have 3 inputs and 3 outputs because size is actually 3, and we created something with si.bus3, which is 3 inputs and 3 outputs. So very powerful API with boxes. And I'm emphasizing here that size 1 has been replaced with 3 here. So component is a very useful technique in Faust. So generating boxes, we can have 2 strategies for program synthesis with boxes. One is top-down from a root node. So here on the right, this is like Haskell or some other functional programming language. So we might start with reduce as our top-level root node, but then reduce needs to take 3 arguments. And so you just kind of recursively determine what those arguments need to be. And sometimes when you create a new argument, that is a function, and then you have to figure out what those arguments are. So when you follow that top-down procedure, then you end up with a full expression up here. So the equivalent thing in Faust with boxes is to say, I want to have a box with 2 inputs and 2 outputs that does blah. And now you think to yourself, I know that box par, the parallel operator, can result in such a box. But if I call box parallel, I'm going to need 2 arguments. Well, those would be box 1 and box 2. And that can result in such a box with 2 inputs and 2 outputs. But now you have to recurse and say, give me box 1 and box 2. And so at the end of this procedure, you would end up with a box with 2 inputs and 2 outputs. Once you end up at a terminal node, just like down here, X and 5 are terminal nodes, and here X and Y are terminal nodes. A different procedure would be bottom-up synthesis from leaf nodes. So it's just the opposite. You start with the leaf nodes down here, and you iteratively create new boxes until you end up, kind of luckily, so to speak, with a box that has 2 inputs and 2 outputs. And just a digression, this is kind of like L systems and generative grammars. So you can go into that rabbit hole and learn more about it. I have some early experiments in this topic of top-down synthesis, where I create a box here, which has 2 inputs and 2 outputs, and I just give it an identifier 12. I randomly flip a coin, and I decide that the box operator that I want to use is box sequence, and now I know that I need 2 arguments for box sequence. And I decide that if I have a box with 2 inputs and 1 output, and a box with 1 input and 2 outputs, then when I sequence those 2 things together, I end up with a box with 2 inputs and 2 outputs. And that meets my specification here of 2 inputs and 2 outputs. So box 1, 2, and 11, which was generatively created, needs to be decided. And so I place that here, and I flip a coin again, and I see that box sequence, it needs to take this argument, box 1, 2, and 10. And I follow this procedure iteratively again, box 1, 2, 10. I flip a coin, I decide that that's going to be the result of calling box split. And when you do this procedure enough times, you can end up with a full abstract syntax tree of boxes, and it could look like this. And what's interesting here is that box 211 is actually used in multiple places, as I've highlighted here. So it was a dynamically generated box that is used in multiple places in the abstract syntax tree. And this code that I showed you on the previous page can actually be visualized as a DAG. And here we have a root node. So that root node is a sequence operator, and it is a box with 2 inputs and 2 outputs, and it has that unique identifier 12. And you can see that it has 2 arguments, which are specified here. And also this box 211, you can see that it flows into 2 other dynamically generated boxes. There's related work on this subject which was presented at ICASP this summer. It's called Blind Estimation of Audio Processor Graph. It's a really impressive paper, and I think it's one of the first of its kind. They're able to take audio and to use a transformer model to predict and generate an estimation of the audio processor graph that was used to create that audio. They're only predicting effects. They're not predicting instruments, but it's an impressive work nonetheless. And once they've generated that graph with the transformer model, they use a separate model in order to predict the parameters that would be most useful for that audio processor graph. But one limitation of this work is that they don't use differentiable DSP in order to improve those audio processors. And also, their set of audio processors is somewhat limited compared to what is available within FAUST. So what I would propose for future research is to get FAUST involved in this line of research, where we are both relying on the FAUST libraries to use our processors or instruments, and then also using differentiable DSP code to improve the predicted parameters. And now the last FAUST representation level is signals, and there's just another API, which I can talk about more in the afternoon, but it's just, you can have sig sign for the sign, like cosine operator, and a pi over 2, so that would result in 1. We add it to 1.5, and now we have an infinite stream of 1.5, and that's the signal API. So there's other work on FAUST and AI, which is the Google Summer of Code 2023 project, where Thomas Rushton contributed code on automatic differentiation within the FAUST compiler. For GSOC 2024, you can propose your own idea by visiting this URL. And there's also the Julia tutorial by Cora Johnson-Robertson, so check out that as well. Final reminders, you can watch my talk on FAUST Day 2023 on Romain Michon's YouTube, where I cover some things that weren't covered in this presentation. There's actually 0 overlap between what I've presented today and that, so do check that out if you're more interested. Also, you can get a head start on the notebooks that I'll talk about in the afternoon by using Jack's notebooks on the DAW Dreamer repository. Please tell me what you're up to with FAUST and Jack's. I would love to help others in using this research. And you can contact me at db1224@princeton.edu. Thanks.
Thanks, David. So what I suggest is that we save questions for the workshop this afternoon, because otherwise we're going to be really late. So yeah, David is going to come back in the afternoon for the workshop. So I think it's definitely easier if we do this like this. So the next presenter is going to be Miller, and he's going to join us on stage. Thank you. Audio is going through HDMI.
Okay. We might have audio. That's all right. I'm mostly going to be theorizing, I think. Okay, now.
Oh, wow. Just going to plug you in. All right. Cool. And then this seems to be working in audio through HDMI.
Well, I'm going to just have to see what I see about that.
Yeah.
Because, you know, Linux has moved on to this thing called Pipewire, and I have
yeah.
not learned how you deal with Pipewire. I think I have to tear everything up and start over.
Yeah, it's...
All right, it's all right. I'll try it just so that everyone can enjoy watching people who use Linux deal with audio. Let's see.
You know, there's less and less theaters where they have a jack.
Yeah. Okay, so now, let's see. So what I've done is I have given myself a PD patch that I use to mix all of my stuff, but that, of course, appears inside Pipewire, which is another patchable hoo-ha. So now what we have to do is kill this. No, come on. And then we stop this. Where is it? Yeah, but... Oh, I better stop this too. Got to kill everything, right? Okay, this, I think I can just Control-C, and this is interesting. Under Pipewire, you throw QJack Control-C, it hangs. You have to throw it the quit signal. And now, we're going to use a little alias I have. And then we're going to try to start over. Okay, so then we go QJack. Here, this allows us to see whether... No, we don't see the HDMI output. Okay, now...
I think I have to change the...
Maybe I have to do this and
Yeah.
say configuration built-in. Whoa!
Yeah, HDMI-C. Yeah, there we go.
All right. Except it just took me away. Oh, that's all right. I don't care about that. All right. So then I'm going to say PD mixer. And this gives me my wonderful thing, which I now have to connect by hand, but that's all right. Now, let's just see if anything happens here. Let's see. This is all got done because I had to send PD into Zoom so that I could do online teaching and have people hear what was coming out of patches. And as far as I know, if you're using Linux, this is the only way you can survive that experience. And now we've tried the test tone, and nothing happens because, right, that's because I haven't done this. And nothing still happens, perhaps because I still have to get into PAW. Then, yeah, so what's wrong with you?
It says, yeah, unplugged display port. Like, what if you...
Unplugged. Cool. So now if I unplug it, I have to start all over.
Like, can you read?
Yeah.
Because I think there were multiple options.
Yeah, okay. Oh, yeah. Configuration. Let's try this again. Oh, I don't want an input. I just want an output. So let's do this. But it's unavailable. And then we got Pro Audio, whatever that is. Okay. Wow. Okay, you know what? If it's unavailable, that's probably because it really is unavailable. Although, yeah, it's probably really unavailable. All right. Okay.
Sorry.
No audio. It's not a problem because I wasn't going to play you any beautiful music anyway. I was going to play you some horrible music. and we've all heard that before. So the let's see, time, right, okay. This is going to be kind of the opposite of what everyone else is going to do because I became aware of artificial intelligence in the 1960s. And so I'm going to tell you some things about 1960s era artificial intelligence. Not really, because actually I've had the benefit of 50 years of extra confusion to add on top of the confusion that existed in the 1960s. Back then there was a figure named Marvin Minsky who thought that the thing that you could do with computers was, since they were logic devices, you could teach them how to think logically because, of course, thought is a logical process, right? By the 80s, when I was a grad student, people realized very well that thought has nothing to do with logic. All right, cool. And in fact, trying to teach computers how to think logically, as in expert systems and whatnot, is not going to get you anything approaching human thought. They still use the term artificial intelligence, which I love using today because one cannot use that term without a certain level of, or a layer of irony. But at any rate, by the 80s, Marvin Minsky, who was already in the scene in the 1960s, I believe, was saying that he was surprised by a thing, which is this. The things which started being called perceptrons, and I think the term perceptron is even older than Minsky, but Minsky and Papert might have made the idea of a perceptron famous, right, in the 70s? I don't know. Back when I was a kid. At any rate, the thing about a perceptron is it doesn't think any better than a logical system thinks. But on the other hand, it's a thing that is differentiable, or actually, even less than that, it's a thing that is continuous, a continuous function of what you do with it, which is not the case of a logical transaction. And so you could hope to solve optimization problems. And the big surprise, which I think the name associated with is Rumelhart in the 80s, is that you can make this thing called a multi-level perceptron, which is a fanciful idea of what a neuron might be. And maybe it's worth delving into that for a second or two later. And you can actually optimize the puppy. And the way you optimize it is by using the thing which I hadn't heard before the 1980s, which is called backpropagation, right? So here, what the picture would be is this. Sorry, this is going to be the opposite of everyone else's talk because you're not going to see any slides. You'll see some patches, I hope, if they work, or if they don't work, I'll still show them to you. And the thing I want to emphasize is is more on a, whatever you say, foundational level of what we're actually trying to do when we make these machine learning systems, right? And of course, today you're not supposed to say artificial intelligence, you're just supposed to say machine learning, or even data analysis or data science, because that sounds like you're being more honest. And my answer to that is perhaps, but on the other hand, I like the irony of using artificial intelligence, so I still use that term. So what you're going to get is about 40 minutes worth of irony, unless you stop me with questions, in which case I will redouble the irony. All right, so here, I'm going to start with a caveat, and this is a thing a math teacher told me in the 70s, I think, which is this. I'm going to start with an example, and then I'll proceed to the punchline. So let's make a unit square. Let's inscribe 4 circles in it. Sorry, I'm drawing with a mouse, which I should never do. And then let's inscribe a little teeny circle in the middle of that, right? Okay, that's a thing, right? Okay, this is high school level math, right? So now let's do this using solid geometry. So we'll go up 1 dimension, so everyone knows where this is going. It's going to be about dimensionality. So we'll make a cube now, a unit cube. And we're going to, I can't draw this very well, but we're going to pack it with 8 spheres, all right? And then, now I'm going to change colors here, how about that? Then we're going to put a tiny little sphere inscribed in the 8 little spheres. Each of them, if it's a unit cube, each of these 8 spheres has a diameter of 1/2, and this tiny thing has an area which is a tiny fraction of the area of the cube, right? Now let's go up to a mere 10 dimensions, which is a small dimensionality in machine learning, whatever you say. And then a funny thing happens, which is that by the time you hit dimension 10, this little tiny sphere inside this cube actually reaches outside the cube. Okay, the punchline being, you think you know about geometry, but when you start getting above about 4 or 5 dimensions, your intuition about geometry is useless, right? And in fact, you can, I'll even show you that this is true. I'm sorry, this will take 30 seconds or so. So here, what the question is, really, is what is the radius of this sphere? And is that bigger than this segment, which has length 1/2? So what's the radius of this sphere? Well, of course, it's the following. To get the radius of the sphere, we draw a segment out to the middle of this sphere, and then we subtract 1/4, which is the radius of that sphere, because the diameter is 1/2, right? So it's just, so this distance here, which is the radius of the sphere, is the distance out here minus 1/4. The distance out here is 1/4 times the square root of n, where n is the distance, right? Sorry, it's the dimensionality. So we'll just say, subtract another 1/4 like that. Square root of n is 3.2-ish, square root of 10, right? And of course, that means that this is about, I'm doing this wrong. Oh yeah, this is about 3, this is a little bit bigger than 2, and 1/4 of a little bit bigger than 2 is bigger than 1/2, and this green segment is longer than that blue segment. Ouch, right? Any questions about this? Someone ask a question, come on. No? All right, well, now, okay, fine. Well, let's make ourselves a nice little autoencoder, right? Autoencoder means we'll put in 1,000,000 pixels, right? And then we'll just squash it down to this tiny dimensionality, which is 512. And then we'll go back and generate our image again, right? That's what an autoencoder looks like. And what are on both sides there are going to be backprop, learnable, multi-level perceptron hoo-has, right? And now and then, of course, all you have to do is just navigate in this nice little 500-dimensional space, which is tiny, right? And, right, it is not tiny. It is far too big for you to believe you know anything about it whatsoever. And that is merely 512 dimensions as opposed to the 1,000,000 dimensions that you started with, which is the space of all possible images, say, right? So, so what do we do when we do machine learning? What we do is we do things at random, in the hopes that our intuition is telling us something, but in the certainty that our intuition probably is telling us something that is 180 degrees away from the truth. Oh, not 180 degrees away from the truth, because, by the way, if you throw 2 vectors out in a high-dimensional space, the average angle is not 90 degrees between them, right? No, it's very close to 180 degrees, and so on like that. Everything you know is wrong, right? Just don't even try to think correctly about this stuff, because you can't. All you can do is stab around and do stuff and see if it works or not, which is precisely what people have been doing with this deep learning stuff for the last 10 years, as far as I've been able to tell. And I won't give you any evidence for that. I'll just let you see if you agree or not over time. Questions about this? Right. 512 dimensions. By the way, how close are we to filling a nice cube of 512 dimensions if we throw 1,000,000 points at it? Well, or all right, I'll be generous, 1,000,000,000 points, right? Let's just, entire music catalog of the world, let's throw it in there and see how big it is in a 512-dimensional unit cube. Forget it, right? So then you have this problem. I'm telling you why this is never going to work, right? I'm going to try to scroll now. Okay, so now what we're doing is something like this. So I'm going to give you, okay, so in 2 dimensions, okay, so here's the thing that people do a lot, and it's kind of fun, right? So we're going to mess with timbre space. Now, the simplest possible approach to timbre space might be something like this. I want to have an instrument which has 2 inputs. I'm going to give it an amplitude and a frequency, a pitch. And I want it to make a nice saxophone sound at that amplitude and pitch. Right? I'm not going to be able to play you my beautiful saxophone sound, by the way, because I don't have sound, but I'll tell you, you didn't have to hear it. It's going to be terrible. Okay, so problem. When people play high notes on saxophones, actually saxophone is not the worst example of this, but you can't just play every possible dynamic at every possible pitch. At certain pitches, you have a very restricted kind of dynamic range. And it might be that at low pitch, okay, so if pitch is here and dynamic is here, so piano to forte, right? Then it might be that your quiet note, that your low notes are all kind of quiet and your high notes are mostly kind of loud, right? Like that, right? And now I'm going to say, well, cool. I'm going to now give it a bunch of data, which is some saxophone player is playing a nice sax solo that I'm going to train this thing from. And what does that look like? Well, it looks like a path that goes wiggling around as the saxophone gets quieter and louder and goes up and down, right? And and it's worse than that because every time the saxophonist takes a breath, you get one of these. Right? But that's all right. We can do things about that. No problem. And now the thing that we're going to do is hook this up to a keyboard, and the first thing we're going to do is say, well, what about middle C at the very quietest possible dynamic? There it is. So here's middle C at the very loud. Okay, so now we're asking the thing to extrapolate. We're not asking it to interpolate at all, right? And why do people use sigmoid-ish so-called artificial neurons to extrapolate functions, right? Oh, okay, and now, remember, we're doing this in 512 dimensions, not 2 dimensions, right? So the truth is much, much worse than what I'm telling you. The truth is actually unimaginably bad, because almost no matter what we give it to try to do, it's going to be doing something that isn't anywhere near the convex hull of the spaces of the points that we gave it to learn on, right? So what we're asking it to do, almost without, what's the right word? Unavoidably, is we're giving it a segment of stuff to learn on, and we're asking, and we're telling it what is true about that segment, and then we're asking it what is true about some point that's outside of that segment, right? Where this is where horizontal is the input and vertical is the desired output, right? And I don't know if you guys did this too, but I decided when I was a kid that all I had to do to get rich was to go to the library, pick up the Dow Industrial Average as it went from day to day, record that or write that down for about a year, which is only, 200 or so trading days, right? And then I'll just make a polynomial that goes through those 200 points, and then I'll just extrapolate, right? And then I'll know whether the thing's going to go up or down, and then I'll get rich, right? I don't know, have any of you tried this? You should have. Well, okay, you need a computer. Well, okay, the punchline is it doesn't work. You probably already know this. In fact, there are people getting rich on Wall Street telling other people that they can do it who can't, right? So in fact, I was solving the wrong problem. I should have said I knew how to do it instead of realizing that I didn't know how to do it. And that also is an interesting object lesson for us all. Now, yeah, I told you I wasn't going to give you any positive results, right? Okay, so let's, so how do brains do this? So going back to Minsky in the 60s, computers, they're hardware, they can do things like simulate stuff. What if we just simulated a human brain and just figured out how the human brain does these creative things that clearly the current state of machine learning is completely unable to do, right? By the way, it's not completely unable to do it. People get it to do things. They just never know why they're getting it to do it, and they never can do it twice on successive days and get the same result. But that's, okay. That doesn't mean it's useless. That actually might, for instance, when you're cooking an omelet, you get exactly the same thing. You never know what you're going to get, but you always get something, right? And usually you can eat it, right? So it's not a necessary condition that we do this, that it be predictable or understandable in any way. But at the same time, somehow you have this intuition that if you could understand what was going on, you could do it a little better, right? And it's clear that we could be doing a lot of these things a little bit better, like not making cats with 5 legs and stuff like that, right? So, all right, well, let's do this. Oh, I'm sorry. Let me fill in one promise that I made about something I was going to talk about. So the thing is this. Okay, multi-level perceptrons. What that is you get a thing which is a neuron, which I'm going to put in scare quotes, right? And the neuron does something very simple, which is it simply multiplies all of its inputs by various gains. And then, sorry, I have to draw a bigger box. After it's made the weighted sum of these things, then it applies this thing called a sigmoid function, which is a saturating function, which does this, right? And then that's your output. And then the multi-level perceptron, okay, that might be an artificial neuron, or it might be called a perceptron, which is, I think, 1960s language for what this thing is, right? A multi-level perceptron, MLP, is just a bunch of these things. Whoops. Oh, no, go away. I want to do that, okay. A bunch of these things arranged in layers, typically, with some sort of connectivity. For instance, the simplest thing, of course, is just to make it fully connected, right? And then each one of these things has coefficients that you have to give it, which are the gains that you put on all the inputs that might be positive or negative. And then what you've got to do is optimize the function. Right? Ah! That's the rub, okay. The easy thing turned out to be how to optimize the function. The hard thing, as we all found out in the next 30 years, was that we didn't know what function we were trying to optimize. So the real thing that you do when you're doing machine learning a la multi-level perceptrons is someone is giving you a bunch of examples, and what you are going to do, how do I get this thing to go away? Sorry. My web browser is throwing me a piece of information, and it is showing up on the wrong screen. Okay, here we go. Okay, so what we're going to do now is we're going to say, look at this nice MLP that I've got. It's got a whole bunch of parameters. So what it really looks like is it's a black box, and it's got parameters coming in, and it's got inputs. And anyway, we also know that the inputs actually correspond to reality. Actually gave us some outputs out. And furthermore, the MLP gives us outs. Maybe I'm supposed to put a hat over that, I'm not sure. And now what we're going to do is we're going to subtract these, and okay, that's going to be a big minus. And then we're going to try to minimize this. Right? Okay, and now the big hidden assumption here. This difference, by the way, is not a one-dimensional quantity. It's not a number. It is a number for every possible input that we're going to train this thing on. So it's a billion numbers, perhaps, right? Because we're going to have a billion examples we're going to train this thing on, right? So what we're really going to minimize is a billion tuplet of errors, each of which is what? Well, it is how far our prediction is from the truth. And that requires a measure of distance. Now, and I'm sorry, do you all know about the problems about distance in large numbers of dimensions? There's a Wikipedia page that has some title about the tragedy of multidimensionality. The tragedy of multidimensionality is if you throw a whole bunch of points down in a million-dimensional space, they're all about the same distance from each other. There's no structure at all that is given to you by the notion of distance. But that's not the worst thing. The worst thing is that we don't even know what distance is when we're talking about audio, because we don't know how different, we have no way of measuring how different one piece of music is from another. Right? We can sort of say, yeah, we'll just take spectral envelopes of time snapshots and call that the distance, but that is not at all, well, that's an approximation of distance which will get us somewhere close to what we're trying to do, but will never get us exactly what we're trying to get to do because it's not really the difference in two percepts, right? The next problem, if you think a billion dimensions is bad, how high dimensional is the human brain? So what is a percept? A percept is maybe a special case of a mental state, right? A mental state is the state of every neuron in your brain. There are about 1 trillion neurons in your brain. Each one has about 1,000 axons popping into it. So we're talking a quadrillion, a million million connections, each of which, all right, so, each of which is running at a sample rate of maybe a couple, call it 1,000. You're clocking about 1 kilohertz, right? So we're talking 10 to the 15th operations per second. Right? And furthermore, we're not just going to run this program for a second or a minute or a week like we would machine learning example. We're going to run it for our entire lifetime, because that's the amount of time we have in order to do our own little bit of machine learning up here, right? So what we find is that there might be between 5 and 10 orders of magnitude, or maybe 15, between what we can get out of the server farm up by the hydroelectric dam in Alaska that Google is using, right? And what we can just do inside our brains for 100 watts. That's the power budget of your brain. You need 2,000 calories to live through a day. Most of it is going to your brain most of the time because you're asleep and stuff. But if you divide it out, it's 100 watts. It's about twice what my laptop is using. And it is about 10 to the 10th faster, or more powerful, I should say. Right? So maybe there's a future in wetware that somehow exceeds what we can imagine doing with silicon ever in the foreseeable future. Okay, so so this idea of machine learning being modeled on the human brain is pulling a little bit of a fast one, because in fact the human brain is so much more powerful than our computer that we would never be able to do anything like what it does, or even like what an ant does, and ant. And furthermore, it's wrong anyway, because the thing about our neurons is they don't act like this at all. Like this, I mean, I'm trying to point at this thing and failing, but this thing, the perceptron, is not like your neuron. Your neuron is clocked, and it has memory, but it also has a pulse, and what comes into it is not values, it is pulses, it's time signals. And what it does depends on the chemical bath that it's sitting in, as well as the relative timing of whatever is whacking into it on its inputs, in a way that's far more complicated and probably far more interesting than anything that our so-called artificial neurons can do. Sorry, I'm just telling you all why you shouldn't be doing machine learning, right? Or, to put it in a positive light, I'm showing you how brilliant these people are who actually get results out of machine learning, despite the fact that we are facing such awful limitations in what we're able to do. Now, differentiability, just because that's the topic of this last couple of years. Differentiability is about trying to make this optimization problem better. By the way, this minimization problem is ill-defined, so what we're trying to do already is probably wrong, but let's do it anyway. And now what we get is the following situation. Okay, so how do you minimize a function? Right? Okay. So first, all right. So here's a nice function, and I'm going to try to find the minimum. This function is the error function, which is over maybe a billion-dimensional space, because there might be a billion coefficients for our artificial neural network that we need to train, right? Okay, and of course, what you do is so suppose, just for simplicity's sake, suppose we're just talking about y equals x squared, right? So what we're going to do is we're going to proceed by gradient descent, which means that we're going to, at whatever point we're at, we'll work iteratively, and we'll figure, okay, look, which way is down from there, and then we'll go in that direction, right? And so, okay, so if we start at point number 1, now what we're going to do is say, well, okay, so my first attempt is 1. What's my second attempt going to be? Well, it's going to be 1 plus, and what it's going to be 1 plus is the derivative of this thing, which is 2x. Oh, I guess I should subtract, and then I'm going to multiply that by some negative gain. In fact, obviously the negative gain should be 1, shouldn't it? So then, right? Shouldn't you just multiply the slope downward by 1, just go 1 step in the direction that you want to go? Well, if you do that, your x2 is going to be -1. You're going to have overshot the minimum by 100%. And then if you repeat the process, you'll get back to where you started. And better than that, obviously that's not converging fast enough. We're just going 1 minus 1, 1 minus forever. Let's just increase the gain to 2, right? All right, then you get 1 minus 3 plus, I don't know what, exponential, right? And then the thing blows up, and then we have to start over, right? Oh, sorry, we have to drop the gain. Let's drop it to 1/2. And then you get a great result. If you say, oh, my gain is going to be a half, we'll get 1 plus 2 times minus 1/2, went straight to 0. No problem, right? So obviously 1/2 is the right number. Now, let's merely push this up to 2 dimensions and see what happens. In 2 dimensions, I'm trying to figure out how to scroll now. Okay, there we go. So in 2 dimensions, and sorry, I can't draw this very well, but here's an attempt at drawing a paraboloid which has one dimension along which it doesn't wiggle a whole lot, and another dimension along which it does. All right? So there's a paraboloid with a presumed minimum here, and we're going to be somewhere out here. And our gradient descent is going to get us real fast down here, and then is going to take forever to work our way over there, right? Now, just imagine this was a billion dimensions, and consider what the ratio might be between the biggest slope and the smallest slope. And you might understand that you might have a great deal of difficulty making your way down to the minimum, right? Because, of course, by the time you get down here, you're going to say, well, yeah, the reason we weren't moving very fast was because that gain that I talked about was too low, right? We have to push the gain up. But if you push the gain up, what it's going to do is it's going to start wiggling you back in this direction until it blows up again. So you're in trouble. Now, okay, so now you can take probably a semester-long course at Stanford or MIT and learn how to improve this situation. But the basic deal is you have to fiddle with it. And of course, really, oh, it's time for me. Any questions? I got 7 minutes for questions. Sorry, I'm trying to provoke you guys, and you're not provocable. Really? Okay. Everyone is just enjoying listening to me.
What is it useful for?
What is it useful for?
Yeah.
Well, all right. Okay, good. I got 7 minutes. Let's see. I'm going to show you something that's really cool, but I'm not going to be able to play you what it sounds like just yet. Where's my thing? Ah! Okay. This is probably going to fail because it's failing. Oh, I didn't initialize. Okay. Now the thing is, all right, okay, good. I'll do this from the beginning. This is an idea. This is an idea due to Sam Pluta, who is a computer musician who graduated from Columbia 10 years ago, maybe, and has been working with the Wet Ink Ensemble, making as their electronic musician ensemble member, which is kind of a cool idea to be one of. And among many other things, he has developed a patch in Super Collider, I believe, that has a few hundred parameters that does all kinds of stuff. And he gets himself a tablet with about 4 different screens on it, and he wiggles stuff around with his fingers and gets through this big parameter space. And now the thing is, well, okay, what if he wanted to be able to get through the parameter space quickly without having to switch screens and move 50 pots so that he can get from one nice sound that he knows how to make to another? And the answer is, well, let's use machine learning to do this. Okay, this is an abuse of the whole idea of machine learning, right? Because what he's going to do is he's going to find 5 or 6 presets, that's to say 5 or 6 sets of parameters that he can load into his super collider nonsense, his madness there. That's got granular synthesis and some FM and some this and some that. It's got all, and feedback, you know, all kinds of stuff, right? And so all you got to do is just find a bunch of good sounds and teach a machine learning algorithm what kinds of sounds you like it to make by teaching it what kinds of parameter sets are kind of cool, right? So here is, in this afternoon I'll get to where you can download this and then you can try it yourselves and see if this is any good for what you want to do. So this is my distillation of this idea down to additive synthesis. So here what you would do, and I'm not going to show you how to train it because I don't want to spend any more time than I've already spent. But here's a joystick. It's not really a joystick because I don't have one, but I'm just pretending, right? And of course I can't have 2 joysticks because I've only got 1 mouse, right? But what I did was I gave it 5 training points, 4 corners in the center, and for each one of them I gave it an additive synthesis instrument amplitude set. So all I've got is a Hammond organ style patch. It has 10 drawbars, and I can just move the drawbars up and down, right? Not as a function of pitch, just straight up single presets. And now, one thing that I thought I wanted to be able to do was just have a quiet, like everybody's at 0, just shut up thing. So I put that up here. And then I just gave it 4 fanciful timbres, right? Here's a kind of an odd harmonic, computer music clarinet imitation kind of a sound. Here's a nice bright sound that's mostly the upper harmonics. Here's a sort of reasonable diapason kind of a sound. Here, I forget what I put. It doesn't seem to, there might not be anything there. I don't think there is. And then what you do is you get your machine, you get your neural network package out, and there's one for, I mean, there's a neural net package for everything now. This is a port of what do we call it? It's the package called FAN, the Fast Artificial Neural Network, which is, I think, 20 years old. Imported into PD by, I've forgotten his name. Daniele, I'm sorry, I can't get his name anymore. I'll find it this afternoon. But anyway, there is a PD FAN package out there, which I have brought up to date and I'm using for fun. And so what I've done is just taught it with these 4 examples, interesting synthesis parameters that I can now quickly move between using only 2 parameters of input, right? Cool. Now, this is a total abuse of everything that you are going to be seeing in the rest of the day, right? Because this is a training set of 4. In fact, the way Pluto uses it is even worse because he has 2 joysticks, which means he's got 4 dimensions, which is already, as I've shown you, impossible to imagine. And he is training it with between 4 and 6 points. So he takes his joysticks and he slams them both northeast, and he puts a sound on that, and he does that like between 4 and 6 times, not exaggerating, right? And then he just trains a neural net on this using some Python package, I don't know, and out comes a synthesizer that he can play. Go figure. Well, it's no more absurd than anything else I've seen anyone do with these things. I mean, you know, this is a 4-dimensional absurdity as opposed to a 1,000-dimensional absurdity. It's no less absurd, and it's useful. So I guess that's a positive note I can end on, which is you actually can do stuff that's cool, but you shouldn't imagine that you're doing anything that is predictable or correct in any sense. On the other hand, music doesn't have to be correct. You know, theorems have to be correct. Music has to have some other quality which is not a truth value. It's not the case that Mozart K500 and whatnot is true and Bach B something or other is false or something like that. No, that's not how music works. And so you can do things like this in a musical context and have it be truly useful for reasons that no one will ever really understand. But nonetheless, it doesn't make it an uninteresting thing to play around in and not necessarily something that can't be very productive for workers to dabble in. The musicians even. All right, and I think I have to stop, so I'll stop because it's time. I think think it's coffee break now. Is that correct? Yes, coffee
Yes.
break. So we can talk about this over the coffee break, and you can chastise me all you want. I don't care.
Yeah, thank you, Miller, for a very cool talk. So we're going to have coffee break now. Again, there is going to be plenty of time this afternoon for questions to the presenters, because they're going to be more, they're going to have more time, at that time. So maybe we can save the questions for later again, and so coffee break starts now, and we'll resume at, I think, 11:20. Is that, yeah, okay, cool. All right, so again, coffee breaks happen upstairs, okay, second floor. Thank you. Okay, everyone, welcome to the next session for today. The first presenter is going to be Celeste Betancourt, and she's coming from Stanford University to tell us about Chuck and AI, basically, right? Okay, well, Celeste, thank you.
Thank you. Okay, so first, thanks for inviting me. Thanks for having me. And contrary to what just Miller said, and he's expecting of my talk is pretty similar to what he said. Because what we are arguing in our lab and what we're trying to find out is like, why are we trying to replace a human brain if it's so good for some tasks, and we just do other stuff that are fun and not that fun to do with a brain, with machine learning, like parameters. Like, what's the point of learning the number for 8 different sliders? You just train a tiny, simple model, and you play with your mouse, and it's like, yes, that's it. Your brain can be focused in the fun stuff. And you don't need to train and fall into this deep abyss or trying to resemble the human brain. So thank you for that introduction, because it's perfect for what I'm going to say. But before I start, I want to run this demo. If someone wants to follow it, you're welcome. This is going to explain a little bit what we're doing in the lab at Stanford right now. This application is called Soundscape AI. Again, we're going to use the term AI just because it's a trend. But and you're going to see later in the talk, we just put CH to everything. We are Chuck, the Chuck team. So we have Chuggins, Chuggle, Chowthers. And you're going to see like, oh, these people loves CH. And it was funnier to have Chai, because Chai is like T, that CHML or CHDA, like data analysis or machine learning. So we just picked AI because it was funnier. Same thing, because Chai makes more sense than everything else. So yeah, so if you're there in this little demo, this demo, before we start with this, was built using Chalk language. And all the things here I'm going to show you today in the talk and in the workshop runs on the web. It's a very good example of all the things I'm going to try to explain, like tiny, small mindset in the AI community. And also it's fun to play. So let's just start with that, and then we jump into the talk. So you should be seeing something like that. This has just a microphone input, something that's called texture and expression. What we're doing here is we train a very small model to try to find similarity retrieval on the input of the microphone on any 2-minute audio recording. In this case, it's like an ambient audio. And then whatever it comes in the microphone, that's going to, the model is going to spit some frames of that audio that are similar in terms of the spectra. It's a very simple collage. It doesn't take a lot of data, it doesn't use a lot of computation, and it's very fun to play. So let's just hit here. So right now it's loading the sample. The model is really not that big. It's more of the sample and the chalk, because the chalk wasm right now is pretty big. Someone can play it right now? Someone that's there? Well, it looks like the internet right now is kind of tricky. Well, also, I have a video of this, so... You can see this, like, if the thing doesn't work, maybe there's too much people trying to download this. I can show the video. Well, as you can see, nothing fancy, just K-nearest neighbor. We're talking again from very old school techniques. We're just windowing audio and analyzing in very, again, old school techniques. But this runs in a phone, it runs on the web, and it's fun to play. Like it's a piece of music that it kind of makes sense compared to other stuff that could be generated using the highest tech algorithms. So this essentially is going to explain where my talk is about. My talk is about how to use the 60s algorithms that are not out of date, just no one ever used it for this kind of stuff, and you just use it. Like, why not? So let's jump into the talk now. The talk is called AI in live coding environments. The live coding environment we're going to talk is Chalk language, which is a product of Princeton University, but now it's hosted in Stanford University. And Pandora's Dream is my own study case implementing Chalk, Chai, Choggle, and Chuggins. You see, everything has CH. So Chalk is the language, Chai is a T. You all know that. But it's our game for Chalk AI. That's why we are not using ML, or because it will not make sense or it will not be funny. Choggle is like Chalk for graphic language or OpenGL. Chuggins is our word for plugins. Well, you can contact me there at my email at Karma. So let's start. A little bit about me. You can find that more about me in that link. celestebetancourt.com. But mostly, I'm a live coder. That means I play on the fly using programming languages, which is a very masochistic thing because I used to fuck it in front of big audiences, and like really bad. Like, how do you just try to think about this example? You put your screen, you put an empty IDE, and then someone is asking you to make music that you need to dance or enjoy. That's a big thing. And most of the times it goes very bad. That's what I mean. That's very masochistic. But that teach me a lot about education. So I'm mostly, again, an educator. I'm a very enthusiastic dancer. I'm not a professional, but I can dance to anything, just on the street. And that's my, in the lab, what I do is advanced research, and CFO, that stands for Chief of Fun Office. So I'm the one in charge of the parties. Because I do algo raves. Algo raves is a very thing, not very new thing, but so you can see a little bit of me. That's me playing a little, that's live coding with a lot of stuff, extra stuff. So my computer is here. My computer is being controlled by this little thing. I'm controlling also this thing, this synthesizer, and this is live coding. Just snippets of what I do. In this case, you cannot see the code because these people who invite me to play this, they were not prepared. Like they were like, you're a DJ. And everyone thinks I'm a DJ. I'm not. I don't even know how to use a DJ unit. I was coding in chalk in that computer that you see there. So they were like, we don't even know what's that, so we're not going to project the code. But most of the time, I project my code. That's live coding. That's my web page. Someone wants to see more of what I do. And okay, so now the talk. We need some context. Am I right? What's Chalk, first of all? Chalk is not the most popular programming languages for audio. It's a DSP, DSL. As David already said, it's a domain-specific language for audio created around 2003 as the doctoral work of Gewang, and the supervisor was Perry Cook. It's not as popular as Max or PD, not as popular as SuperCollider for many reasons. One of them is the language was almost dead by 2016, 17. Like no one was taking care of the language. The issue list was just growing and growing. No one was answering. So people just start abandoning Chalk. But we are now again working on it. Also, David Brown is part of the team. So this is Chalk. It's a new, in 2003, it was a new audio programming language for real-time synthesis, composition, and performance, which runs on community operating systems. Chalk natively supports concurrency, multiple simultaneous dynamic control rates, and ability to add, remove, modify code on the fly. That's live coding. In 2003, the live coding thing was not a word yet. So it was used as on-the-fly programming. Okay, I'll continue. While the program is running, without stopping or restarting, it offers composers and performers powerful and flexible programming tools for building and experimented with complex audio synthesis programs and real-time interactive control. That was the promise in 2003, that it was kind of true. Some things are true from here. Some things never happened. But, well, first, after 20 years, there's a lot of things that have changed. And well, we have a big team of authors. You can see the whole thing here. I just don't want to forget anyone because I'm just part of this team. But Like the original team was Gil Wang, Perry Cook, Spencer Salazar. After them, Rebecca Fibrick, author of The Wakinator, which I'm going to talk a little bit later, was part of the team. Jack Atherton as a Stanford student, Dan Truman, Princeton, Ajay Kapoor, and many other people, including me, are working on this language. This year is the 20th anniversary. One of the main features of the language is this idea of the time is now, which implies Chalk is very good for control things. It's one of the best languages for controlling very precisely what you want to have in your program, sample by sample. Contrary to every other programming language, everything runs without you taking care of timing. You just connect a sign to the DAC, and you're not like controlling how much time that's going to happen. That's PD approach. You just connect it, and it will sound forever if you just don't unplug anything. Same for every other language. Like they are focused on some other things. Chalk main thing was this idea, time is now. So you need to control what's going to happen in the software at a sample by sample rate. This is just for the ones who don't know what's Chalk. Chalk has a lot of the SDK, which is the synthesis toolkit. This is originally by Perry Cook, a lot of Eugene's. Then it was expanded using Chuggins, which are plugins in Chalk. And these are the new ones. Like we have Chuggle, which is OpenGL Chalk, and lately we incorporated the Rave from IRCAM, the autoencoder, and many other stuff. But now, again, I'm just going to show a lot of things because this is more like a study case, so it's not a very technical talk. So I'm going to show what we are doing again with AI. AI. This is Gewang, and he's going to show us how to use Chai, the new Chalk for AI. Same idea of the Soundscape AI, like just analysis on an audio and then windowing that audio compared to the spectral characteristics of the input, and then retrieving audio windows from the original audio, in this case the Beatles, as he said. Not very fancy thing, but very like a good toy to play. Okay, so let's continue. What's Chalk? To finish the introduction, it's also a standalone software that can run in every operating system. It runs in a terminal, as a terminal software, or can run in a mini Autical, which is the integrated development environment developed by Spencer Salazar. But we also have another, like an ecosystem. The ecosystem is Chalk for Unity, which was a very strong thing until Unity decided to go hell and send every developer to just do whatever you want, but just pay us or something. So this was very important for us until this year. We also have a Chalk for Unreal Engine. We have Chalk for Touch Designer. We have a Chalk for PD, and we have a Chalk object for Max also. Plus these very specific objects, we can just host a Chalk in any C++ or JavaScript project. And one example of that is WebChalk. I'm going to just quickly show this. What is WebChalk? It's one of, this is WebChalk. It's just a JavaScript WASM file that's running in a web. And you can do Chalk. And that's pretty easy right now. Like we just fixed a lot of the problems that were not allowing this in the past. Okay, so, okay now, another demo. What do I do with this kind of technology that's not new? As Miller already explained, it's from the 60s. And how do I use this in a live coding environment? Like, how do I do music with this? So I'm going to show a little demo. This is the demo I'm going to try to explain you in the workshop. This just uses a very, very simple algorithm that's called hidden Markov models to do a task that is quite good for that kind of experience. Before hitting play, I'm going to try to expand the idea. If you hit generate in any like music, deep music, one of the engines that Google or Meta or any of those companies have released, you will find that they are trying to generate the whole audio sample by sample. So you type like, I want a techno song. You're expecting to have like the whole audio sample by sample, and it should sound as a master mix master composition. But that's very difficult, as Miller was already trying to explain us. Like you're dealing with huge amount of information with high dimensionality and many other problems. Like we don't even know how to extract the audio perceptual things that we perceive. But as humans, we are very good for that. So what's techno? For example, techno, it's a type of that music that is very easy to understand if you understand a little bit of music. The kick in the techno, it's a very simple thing. All the time sounds like this: boom, 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 boom. That will take a human brain to understand like 20 seconds. If you hit play in any techno song, you will see like, oh, that's the kick. The hi-hat, there's two hi-hats. One will do the contrary. So it's like boom, 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 boom. And there's another hi-hat using. Well, for any human, that will take no effort at all to understand. For a machine learning AI algorithm, it will be very hard. As we already know, it's pretty much a lot of energy consuming, time consuming, and the results are not good enough yet. But this kind of approach, like just using a hidden Markov model for helping me give some variety to my ideas, it's quite easy, because a Markov model, if you feed the Markov model saying, this is a drum in techno. A drum in techno is just a sequence of triggers. The kick is on, the kick is off. The kick is on, the kick is off. The hi-hat's off, the hi-hat's on, the hi-hat's on, the hi-hat's off. And then you just feed the sequence into the Markov model. And then you use that information to predict outputs. It's very cheap computationally. And it's, sorry for the word, freaking awesome. Because it's very simple. You just need triggers. Trigger, 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 trigger. And that approach is the one that we're trying to use. So I'm going to show the example. This is a running example. This is not a video. Let's hope it works. Okay. This is being generated real time. And what we're seeing here, it's the sequence that the algorithm is generating. Everything's being generated by Markov sequences. Everything. Okay, so that's, again, the whole point of this talk. Like, we're just trying to reduce the problem to something that's very low dimensionality, with a very low dimensionality, so we are very just playing with absurds that are smaller than the big ones that are dealing some other companies, because we don't even care. We're just trying to use this kind of tool in a very more creative way. So now I'm going to jump into the study case. How do we get here? This is Pandora's Dream. There's a screenshot of one of the implementations we have been using for all this new stuff that is happening in Chalk. This is just a C++ application that embeds Chalk as an audio engine, can send databases as like code as databases to WebChalk. It can run JavaScript code. It can run C++ code, C# code, in a custom language that's called Pandora. But the whole point of this is like, what do we need from Chalk to have tools like this? This is the description of the idea. When I was talking to Go, like, I want to build this, so we need to improve the language in a way that's possible to do this kind of stuff. So I was just probably drunk with him, and I started describing this idea. It's just about the Pandora's box. Pandora has been in these places this year. That was in Bean Counter Hall. Then it was in Nîmes in Mexico, Reykjavik with the Intelligent Instrument Lab. That was in Eclectic in London. That one was at Karma. So these are just iterations of testing the like proof of concept that Chalk as an audiovisual engine plus the help or these simple algorithms can be a very powerful tool for creativity. We don't even care if it's very powerful to predict outputs or generate a whole audio in real time with real features. We're more interested in how this language can provide an artist, a human artist, with tools to play. So now the description of the whole thing. Now this is like the most important. The next two slides are the very important ones. So I'm going to stay in here for a while. Pandora's Dream is the case of a study that I put together to work on Chalk as an excuse to develop more new features. New features, as I already explained, more chuggins, which are plugins, language improvements, and many other stuff. So what we find is things that are already said and were already said many years ago. For example, the first one was said by Perry Cook itself. This is not an actual quote, but he talks about this a lot in many of his papers. Focus on the piece composition, not the tool. I don't want to be replaced by a hit button and maybe sounds techno. Like, I don't care. Probably is good. I really don't care. I don't even want to do it because the joy I'm getting out of this is that I have a tool that helps me do what I want to do. I don't want to hit play and just hear music, random music that's being generated. Makes no sense to me. In this case, the approach is the artist. Like we want the artist to focus on what he's trying to do and not the tool itself, not the AI stuff. We're trying to make a very strong audiovisual correspondence if it's possible. You already saw that in the video. Like the AI model, AI, again, big quotes because this is just a hidden Markov model, which will not be AI. But I will love to say it's AI. You can see what's doing. Like you can see the triggers, the on-off switches, and that's good for understanding because I do live coding. I want the people to understand what I'm doing. This is a very nice approach we're trying to do, which is rebuild, rethink, retrain, remap, rescale. What that means is if the model is too big to handle even consciously, we just scale it down to less dimensions and less dimensions until you have like 2, 3, 4, 8, maybe no more than 32 or something. No more than 32 faders because you're never going to use more than that. But in that sense, we have 3 approaches. One is live coding, which Chuck is very good at. GUIs, creation of GUIs, like Chuck doesn't have this in the original implementation, but we're working on that because we saw other softwares and languages that use GUIs and are very good with that. Also hardware, just plug in hardware and see what it works. Train the modeling on hardware or whatever you want to do. Just thinking that some languages and tools are better for some tasks. Live coding is very good for some things, but then if I want to change from techno to reggae, it's going to take me a lot of time to type down the rhythm. And in that case, AI makes sense because you just type down, like switch from techno to reggae, and then the algorithm can just pull that out of a database and just put it, like plug it into my model, and that would be very fast. So live coding using AI approach, in this case, it's very useful if I want to switch ideas. So techno to reggae, reggae to pop, pop to whatever, switch the synthesizer. When I say switch the synthesizer, we're not using what David was describing, like switching or remapping the whole synthesizer. We're thinking more in what Miller was describing. You have an already made synthesizer, and what you're doing is playing with the knobs. So you memorize, the algorithm learns positions in the synthesizer, and then you go back to those positions. And that takes us to this idea of small, tiny models, which was described better in this paper, but these people, especially small data mindset, which just means keep your mindset small, dimensionality small, so you can understand what's happening. If you need to go up, use your brain. If it's something you can solve in a very low dimensionality, you can use machine learning, AI, and that will help you a lot. And then that takes us to this idea of AI should be explainable. That means if we don't even know what's happening, we're just playing a video game, kind of. Like just hit play and something's going to happen. Probably it sounds like techno. Probably not. But we don't care. We want scientists and people and artists to understand what's happening. So it should be explainable. And for that reason, we redo the Chuck language. Chuck language was a very static thing. I told you this in the 2000s, then 2010, it was almost dead. But we already start doing a reconstruction of the language in many senses. And that includes all these things that are like the new stuff. Some of these unit analyzers are old. They were implemented by Rebecca Fibrick when she was doing her PhD at Princeton. But we update the list with some of the new things. So like from here, this list you see, these analyzers are, this one's old. This is from the old implementation. But the spectrum chroma is new, spectrum flux is new, the kurtosis is new, the MFCCs are new, RMS is old, the roll-off is new. Some of these are new. Like we just implemented this like 6 months ago, just to add more tools to the artist. We implemented this new plugin that's called Chai, which is Chalk for AI, but literally, it's just what Miller was explaining. We are just using very simple things like these hidden Markov models I just show you in the demo. This support vector machine, simple stuff. K-nearest neighbor, very simple stuff. The difference between these two is like this is untagged and this is tagged. So that's the one I'm using for my live coding performances. I said reggae, that's the tag, and then it retrieves me a bunch of arrays with information, nothing fancy, and the multi-layer perceptron, which already Miller explained deeply. Also, we implemented the Wekinator, which is a very famous AI machine learning tool that has been very popular, but it was a GUI program standalone, so we implemented as a Chalk object. So right now, Wekinator can run inside Chalk, and you can do anything you can do in the original version on Chalk. And that has been very funny. Other stuff we have been implementing just for the use of this approach, and very important is this symbolic data approach, because it's cheaper, faster, and human readable. If you try to analyze the chords in a song computationally, it means you need to do a lot of FFTs in a window. Frame by frame, you need to compute the centroid, the chromas, the spectral chroma, and try to see if the chord exists. If the chord exists, it's an approximation, because it's not really the chord, it could be an inversion, many things. But in symbolic data, that's very cheap, because for a computer understanding C minor, it's very easy. Like that symbolic data will go back to this is a chord. Like for a machine learning algorithm understanding, like you have this chord, it's a chord. Like what do you want from this? You're not trying to analyze the audio real time. You're trying to analyze the audio as a chord. And that approach is very, very useful. So we implemented the MIDI in and out, XML in and out, music XML in and out, and we're working on YAML format. Because training our models in our little models using this approach, it's way faster and way more productive for an artist like me. In my case, this is my study case. So again, in scale, if you try to do that using the Fourier transform approach, you need to do a lot of analysis, a lot of dimensions, probably 1,000 dimensions per frame, and that's going to be a lot of data. But if you're analyzing a scale, that's a MIDI scale, it's very easy because it's going to be like 60, 62, 64, 60, 60, 64, 62, 60, which goes back to why it's important to have a hidden Markov model instead of a very big analyzer plugged to a very big machine learning algorithm to try to take that information out. And finally, we add a lot of syntactic sugar to the language, which I'm going to show in the workshop this afternoon. Things like operator overload, because that's very useful for this kind of task. We add new for loops that are easy to implement. We added the auto type and many other stuff. So I'm going to show that in the workshop. And I think that's it. Let's see everyone.
Yeah, thank you, Celeste. I think we're going to save questions again for the workshop this afternoon. Like everyone has a lot of things to say this morning, so so I guess that's good. So the past three presentations were mostly about programming languages in the context of AI, so computer programming languages. The next presentation is a little bit more open, you know, and also this is why that's the one that we're doing just before lunch, you know, because you kind of need the little cherry on the cake. So, so this is the last presentation for this morning, and after that we'll go for lunch.
Le son, normalement, par là, je l'ai mis. Mais là, comme c'est dans le note, normalement, il ne peut pas y avoir de souci. Ok, puis ça, je le mets dans la poche.
So hello everybody. I'm a musician based in Paris. I don't code, so sorry, nobody's perfect. But I've been working with researchers, with a research team led by François Pachet, that you may know. At Sony CSL first, I entered in this team in 2015 as a musician in residence, so that means that my role was to help the small team, we were like 7, to help the researchers to build tools. And the technology that we were developing at this time was flow machines. So I started to work with flow machines, and I had some results. The first thing that I made to play with this tool is to feed the machine with the lead sheets of my favorite band. It's the Beatles, because I know very well the Beatles, and so it was easy to see if the result was interesting or not. And I got this result that was Daddy's Car, a song in the style of the Beatles, so it's not really the Beatles, but like the song of a fan of the Beatles. And then I started to experiment more in a creative way with flow machines, and I did the first album, Hello World, made with flow machines, and I invited a lot of artists with me to play with flow machines tools. And then I continued to experiment with the team on other tools. Flow machines was really dedicated on composition, the composition phase, but then we get interested in more in like arrangement phase with orchestration and sound production. So all the projects that you see here are really linked to my experiments with the tools. This is the Beatles.
Je pense qu'il faudrait changer la sortie audio.
Ouais.
Pour lui dire de. Sur les Mac.
C'est là.
Ouais. Je suis pas trop sûr de lui.
Son. HDMI. Okay. So I think that you heard the song. So it was like it was just the composition. It was symbolic notes. And what I did is a short, a very fast demo, imitating a bit the sounds of the Beatles, all the choirs and everything. But it's really based on lead sheets, and the technology is based on Markov chains. So when I wanted to experiment more in a creative way, I challenged the machines with the smallest corpus that I can find. is just 2 songs. And that's why I think this technology was interesting. It's because you can really, you have the control of what you give to the machine. And it's very exciting when you are a composer to know what you put in the machine, because you dream of a result or you expect the result. You can make all the combinations that you want, even the craziest. But at this point, I wanted just to experiment with a very small data set, very small corpus. So I fed the machine with only 2 lead sheets, and I will play the 2 lead sheets, and then I will play the result that I got, just 9 bars of a melody and chords. So the first song is, maybe you know this song. And the second one, and I choose this second one because it's like a bit similar to the Jungle Book song. And I got this result. I was amazed by this result because I couldn't think of all those notes and very strange chord changes. It starts with like a B flat 7, very, very strange, but still very nice to my ears. And what I find interesting is that it keeps the musical qualities of the source, and there is no plagiarism, even if it's like sounding more as like the first song than the second one. But and then I continued to experiment, and we made a whole album with this Flow Machines technology. Oh yes, I want to play the same song sung by Kyrre Kusmanson, who sang the song and wrote the lyrics.
Aurora, starry sky, a holy temple, a mountain high. Gods of ancient times, heroes, battle cry, lovely children shed their dreams, angels cried, tears of moonbeams, I saw and I know all there is to know.
Yes, and the chorus part, I fed the machine with jazz standard songs. So you hear that there are more chord changes, and it's a bit different from the verse part. And so on, we did this album. It was a great experience because all the artists, the composers that I work with, we always were very excited about what the machine would create from our data set, from our corpus that we fed the machine with. And then we moved to Spotify, but we were still the same team, and we focused on the orchestration phase of a song creating process. And we built this orchestration tool that was able to automatically adapt an existing arrangement to a given song. It's a MIDI to MIDI tool, so it's very, very easy to work with, very, very flexible. And so we were at the very first stage of the tool, And I wanted to experiment it again to give the feedback to the researchers and optimize the tool. And I had a song in mind that I loved and listened a lot. It's a song sung by Pete Seeger. He recorded it in 61. And this is a song without any arrangement, without any accompaniment.
Black, black, black is the color of my true love's hair. Her face is something wondrous fair, the purest eyes and the daintiest hands.
I love this song. I find it great. It's a very old song. It's a traditional song from the Appalachian. As I worked with, I fed I took this song as we can say the target. I annotated in MIDI, the melody in MIDI to play with the tool because it's MIDI to MIDI, so it doesn't work with audio. And I searched for a very, very contrast style to play with, and I thought of bossa nova style. It's really sophisticated harmonies, and overall you have the strings orchestra that are even more sophisticated on those sophisticated harmonies. So I thought that it could be interesting to have this contrast between a very, very simple melody and a very sophisticated harmony. So I took a string score that I did for another song. The song, maybe you know, Estate. It's a song that is sung by in Amoroso album from Jean Gilberto. A great arrangement, yes, by Klaus Ogerman, who is the master of this style and the strings orchestra arrangement. So I will play now the arrangement that I did with on this song Estate. So you hear very, very sophisticated harmonies. Now, if I play this arrangement with Pete Seeger's song, it will be, I think, awful.
Black, black, black is the color.
Okay. So what it does, it analyzes the target, so the melody of the voice, and it analyzes the source that I give to the machines. In this case, it's the strings arrangement that I did, and it will automatically adapt this string arrangement to the melody.
Black, black, black is the color of my true love's hair. I love the ground on which she stands.
The last chord is really unexpected. And that's what I like when I play with those tools, is that first, the interaction is great because you can feed the machine, as I said, with the material that you control. And you have unexpected result that you couldn't have made by yourself. And that's because if the result was like conform, I don't know how to say, but like normal, I could have made it very easily. But this is really special. And I was so amazed by this result that I did an entire EP with 5 songs reorchestrated by this tool. It was songs, traditional American folk songs. And I fed the machine with very various sources, like songs arrangements from, or mass from the 16th century, Elizabethan music. So I could play with very various styles. And for this song, we went in studio and we hired strings player to play the AI arrangement. AI, it's not AI, it's like the arrangement made by the tool.
Black, black, black is the color of my true love's hair. Her face is something wondrous fair. The purest eyes and the daintiest hands. I love the ground on which she stands. I'll go to trouble.
And you can listen to all the EPs on all the platform if you want. And maybe the next and last example of all the tools that we developed and the music that I made with those tools, it's like a smart sampling tool that is able to adapt automatically an audio file to a MIDI file. And I was experimenting with Pierre, maybe you know him. He was at the Citerial team at Spotify. And we started to experiment just with a random thing, random piece of music, and we choose this Fugue from Schubert as a MIDI target file. So I searched on the internet for something very unexpected. And I got this result. So when I got this result, I was so amazed that I looped it. It's like 8 bars, and I created a song from it. So searching for lyrics, melodic voice, and everything. And I wrote a song named Océan Noir, available on the platform you can listen to. Maybe I can play just a few.
Océan noir, j'entends les baleines dans un acouphène. Ici aucune vague n'accoste.
So it's the idea, you see, like experimenting, be amazed and do something with it. And next, yes, the team was closed, so I was alone in my room, and I continued to experiment with the vocal cloning technology. Maybe you surely have heard about everything, all the fake Drake songs and everything, but I find it like very impressive, but not very interesting. What I find interesting with this technology is to do hybridization. So I experimented with the RVC technology, maybe you know, retrieval voice conversion, with just a Google notebook. And I created a data set with my favorite singer, Chet Baker. I fit this data set with 6 songs from Chet Baker and 6 songs of mine. And it's like a fine-tuning. You sure know this kind of technology. There is a big model, and you fine-tune with the data set that you choose to train. So I will show you how the steps and how I hybridize it with a very short music example. So here is Chet Baker singing My Funny Valentine.
My funny Valentine.
Me.
My funny Valentine.
And the result with the hybridization.
My funny Valentine.
So what I find interesting, and I experimented more with this tool, what I find interesting is that, for example, the A are much more opened than in France. So it's like a bit closed, but if I sing it with the voice, when I hear the result, I hear more open A notes, A words, syllables, I mean, and so on. I know that if I sing with my vibrato, I will have a different result if I used a model with, for example, a jazz female singer. The vibrato will be like enhanced. And what I find interesting is with this tool is that you can really enhance your voice, explore different kinds of way to sing, and you can, what is interesting is that you can also predict a bit the result because you know the voice that you're using as the clone and you can sing it in function of this voice. So I think it's a great tool. And there is also a version, real-time version, maybe you know this. And I had a good surprise when I played with this real-time version. So sorry, the video is in French, but maybe it's not important. The music is more important. And that's what, from my very, very first song, what moves me is not only creating music, but it's also being creative with the instrument. That means changing the function of the instrument. Make it like tweak it, change it. And here is again an example. I did it like just this week. I was playing on the piano, you will see, and I had a good surprise. And I think it can be a nice example of diverting an instrument from its intended purpose.
Voilà, je voudrais partager avec vous ce moment où je détourne un outil, un instrument de son usage pour faire quelque chose que moi je trouve super beau. Donc là, ce que vous voyez, c'est un outil incroyable qui est, je pense, l'unique au monde de clonage vocal pour le chant en temps réel. Donc là, j'ai fait un modèle en hybridant plusieurs voix de chanteuses de jazz et vous allez entendre ce timbre de voix quand je vais chanter dans ce micro. Alors, je peux chanter en même temps. Il y a un petit délai. Et là, vous entendez? Alors moi, je vais faire chanter piano.
So I think it's a nice way to explore, and I will explore more with other voices, other instruments, and maybe there is something that will happen with this. And now I want to jump into, because it's about language here, and I want to share my experience with text-to-music tools. You know all those tools, and maybe you know how they are trained, and I find that the way they are trained is really interesting. For example, but I think it's the same for Stable Diffusion and Music Gen. For Google Music LM, they train on a music cap dataset composed with 500 music text pairs with rich text descriptions provided by human experts. So the music is described as, for example, you have an example here, a low-sounding male voice is rapping over a vast, fast-paced drums playing a reggaeton beat, etc., etc. Okay. And I think there's a lot of things that are missing if you are like in a creative process, because you can have, for example, a song with a chord sequence that you are working on. For example, songs with a chord sequence like A minor and everything, with a fixed tempo and everything. So constraint, your own constraints. And if you ask, I ask, for example, to Stable Diffusion Audio text to music, a piano playing 4 bars, time signature 6/8, fast arpeggio at 100 BPM and on a chord sequence that you see. And what I got is that. So, not very interesting, and I can't really play with it. I can still start a song with text description, but it's like to take or to leave, and I can't really tweak the result. I think it's not interesting when you are in a creative process. But maybe later, I don't know. Maybe they need to train pairs of text to music with more informations, like musical informations. GPTs, I'll try also this, because I want to find the tool that will like inspire me in terms of composition. But so I played with the GPTs. You know, it's like it was launched 10 days ago, and the difference between ChatGPT and GPTs is that you can feed with more material. It was limited. Now you can feed with a lot of amount of data, but I don't have a lot of data. I just have 14 songs from my first pop band in the 90s, Lily Cube. Maybe you know this band. I play a bit one song that we did in this album.
Faire une virée à deux, tous les deux sur les chemins.
A refresh song. So I fed the machine with ABC language because from my experiments with ChatGPT before, MIDI is not very, the result that I got was very bad. And I don't code, as I said, so I should use Music 21 and a lot of tools to analyze the music in a relevant way, but I can't do that because I'm not a coder. So I fed this with ABC language, and I asked to generate a song in ABC format in the style of Lily Cube. So I had an answer. He said that yes, it's very yes. You see, creating a song in the style of Lily Cube, a French pop group known for their melodic and poetic style, can be a delightful challenge. So he did it. He created a song. The name is Rêverie en bleu, and you can listen. There is no. I don't have the audio, but it's interesting because I have a text, I have lyrics, and I have chord sequence and a melody, but it's kind of boring. I don't have all the chord changes that I do, all the modulations that I usually do in my songs. It's like, okay, not inspiring, just okay. But yes, maybe later, or maybe if I feed the machine, if I create a model, or if maybe that in the future, maybe in the very next future, we will use this kind of technology to help to compose or to inspire. But for the moment, I should know more about technology to do it. And the promise that was made by OpenAI to train your model without being a coder is not effective today. It's like we have to wait a bit more if you are not a coder to play with GPT. But I continue to play with ChatGPT with Faust because I'm not a coder, as I said, and maybe that ChatGPT could help me to create sounds with the Faust language. And I fed the ChatGPT with a prompt including an existing code. I can play this sound. Okay, but yes, there are some things. So I asked to create a variation on this sound, and I got this. Sounds like Amar 808, maybe you know this. So that was great. I was like, okay, I can play with Faust. And I tried just text to Faust. Can you write the code for a sound of the marimba DX7 preset? And I got a result that I can play. Where it? Okay, it's there. Wow, it's not easy. Where is the? I don't see. Sorry, I will just. Wait, okay, it's there. Okay. So I got this. Doesn't work? Yes. Okay. Marimba. Not bad. Not great, but not bad. So, yes, what I dream about is now it's like a DX AI powered by Faust. The idea, because I love this synth, maybe you know this synthesizer with all those algorithms, and I learned to play with the DX7 when I was 16, and I bought like a guide to program sounds on the DX7, and it showed, for example, that the bell is a sound that have harmonics, very powerful, a lot of harmonics in the attack, and the fundamental note is low, is going like that, and this book showed how to create it with a DX7, and I played a lot with this DX7, and I found the sound of the DX7 amazing. I love it. And also, I find it really interesting in terms of programmation to create sounds, realistic or not. And I imagine a tool that do like audio to Faust. using the DX7 FM synthesis. And for example, like take a bell sound. And I imagine a model with pairs of audio and false corresponding code. And then I think it would be great. And we had discussion with Diane about that, and I said, do that. Always like that, there is an existing project with the DX7. It's a differentiable FM synthesis with musical instrument sounds. There is an archive, it's a paper, it's a project that can, the idea is to transform real sound into FM synthesis sounding, but I will just share with you the examples that are provided here. No, it's here. Flute. And the DX. Okay, that's nice, but it doesn't sound like the DX7 flute sound. So my idea is okay, always still okay, because I think that Faust is more adapted to that kind of project and to keep the qualities, the qualities of the DX7 sound. So yes. That's all for me today.
Thank you, Benoit. I think we can take some questions because Benoit is not going to be giving a workshop this afternoon, and it's time for lunch break. So, do you have any questions? So, yeah, now you have to make what he said, right?
Thank you, Benoit. Already saw the presentation yesterday, but it's very nice. Have you any plan to work with the real-time voice conversion? And have you tried to, because you were wearing headphones have you tried to feedback her voice, so to speak, and to see what happens instead of the piano plus her voice? Just curious to know. And do you have any plan? And how do you plan to, if you have any plan to use this kind of tool in maybe in next album or somewhat?
Yes. What you mean by feedback?
Feedback is having the loudspeaker with the voice feedback into the mic and then reanalyzed by the voice.
Okay. I didn't try it, but I will try it definitely, yes. Yes, I think that I have a live performance that is booked in June in Paris. So I will work on the project using this real-time voice conversion tool. And I will explore more with those captation of instruments with this technology. I think I will do like an EP or something like that because there are lots of things to explore with this kind of sound and translation, real-time translation between instrument and voice. Yes.
She sounded like Mylène Farmer a little bit somehow, like I thought. But
yes, but it was like a lot of Julie London inside.
Ah, okay.
Julie London is very, very soft.
Yeah, very soft, yeah.
Yes, so that's why.
Cool. Any other questions? Yeah.
But I think I should try with horses, like other kind of sounds.
Thanks a lot, very interesting. I have a question in terms of like copyrights. So if you train the model with the song of artists, both for lyrics or for style, do you think that there will arrive a day where you have to like, the copyrights must be paid or something like, you know, like in sampling, when at the beginning of sampling, everybody was sampling everybody, and then there were some issues and people had to pay.
For the vocal cloning, you mean?
For like everything, like if you train a model on the song of like the Prodigy, do you have to pay the copyrights to the Prodigy or not now, but maybe in the future?
Yes, sure. It should be because, as you said, there are more and more like small data set used to very specific tasks, and I think that it will be possible to have transparent kind of system that will give money to all the right holders. It should happen, but very hard to make.
Hello, Benoit. I am a software engineer myself, and I find all these tools quite fascinating, but on an ethical level, are you confident that the humans still have room in the field of music in the future, or are these tools not going to produce like increase on the production of the market, or how to put it? There's two effects I can see. The amount of musical production is going to increase, I guess, because all these tools are going to facilitate the access to musical production. And also, regarding human performance, it seems that humans are going to be more increasingly assisted by software and tools. So are you confident for the future, or are we going to see AI made for AI, like robots making music for robots in the long term?
No, I don't believe that. I believe in creativity. I think that even if the tools are really powerful, more and more powerful, and I still believe that creation is creating something new. And creating until the end, like it's finished, I want to release it. This is the creative process. It's always the same. I think that maybe the kind of musician will change, but it's always been the case since the beginning of music creation. What I think is maybe that instrumentists will be like impacted. Like, for example, I can imagine that in the very next future you will have those with assistants like Copilot who will be able to feed the gaps. If you need, for example, a bass line, I think you will be able to complete it with AI, and so you won't call your friend who is a good bass player. That's kind of problem that we maybe will encounter. But for creativity, I think it will be it will always exist. And for all you see, the text to music, when the quality will be okay, because for example, for the moment it's not good, but it can be a danger for all library music, because if you have a low budget, you will be able to just with the text description have an average result that is okay for your I don't know, image or video, whatever.
Cool, thank you. Thank you, Benoit. I think we need to stop, because otherwise we're not going to have enough time to eat. So thank you so much. So we're going to take a break for lunch. Again, there are three options that we recommend. If you want to get a not so great burger, you can go to Ninkazi. If you want to get a not so great pizza or kebab, you can go to Universe Cafe. And if you want to get a great sandwich, then you can go to the bakery. We'll see you at 2 p.m. Thank you.
D'accord.